Alright, welcome back to our series on matrices. This time we're going to be doing some applied math. It's kind of a shame I don't do applied math more often. It's kind of my wheelhouse. But today we're going to be talking about DC resistor networks and how you can use Gaussian elimination, which we learned last time, to find the missing currents or voltages in a very basic type of circuit. Alright, now we're about to give the world's shortest account of electricity and magnetism up to this point. Okay, so you know there are charges. There are two kinds of charge, positive and negative. Like charges repel and opposite charges attract. Well, these charges give off something we call the electric field. They generate a field around them, which is like something which has a value at every point in space. Right? It has some strength and it has a direction too. And this electric field tells you were you to put another charge, specifically a positive charge by convention, were you to put another charge in the vicinity of this charge, with what magnitude and in what direction would that second charge experience a force of either repulsion or attraction. And this electric field is well defined at every point in space. It varies continuously. And actually light is just the wiggling of this electric field really fast. Alright, so if you're a point charge, you might ask yourself, is there a way to know in advance if I take a certain path, whether the electric field will help me along that path in the force I experience, or whether it will deter me along that path? Will I have to do work against the field, or will the work be done by the field to boost my motion? Because you can imagine if the electric field is varying from point to point, then sometimes it's going to be sort of helping you. It's going to be sort of aligned in the same direction as your motion if we're going along this curve. And at other points, you're going this way and the electric field's pointing in a totally different direction and it might not be helpful. So if you're a little philosophical point charge, you might ask yourself, can we keep track of how much total it is for or against you over an entire path? And this is the idea that leads to V, which is the electric potential. You've heard of its units before. It is measured in volts, right? It is voltage, electric potential. And very nearly, voltage is to electric field as potential energy is to force, if you're an analogy person. And there's a special kind of field we want to consider here, and that is a conservative field. So if I'm going along this path and the voltage difference between these 2 points is some certain number, but then suppose I take a different path, same two endpoints, but I take a different path, and suppose this voltage difference between the 2 points does not change. And suppose that this is true for any path that I take, that as long I can take some wild and crazy path, as long as I start here and end there, the voltage difference is the same. This is called a conservative electric field. Conservative meaning is a gradient field, if you know what that means. But yeah, it's a special kind, and it's the kind that we're going to be making the approximation that is the case in every circuits problem. Because if not, then Kirchhoff's voltage law will not work. The last thing we want to talk about is conductors. Conductors are assumed to be completely equipotential in the sense that the potential difference between any 2 points along a conductor, I drew a little wire here, it's supposed to be a cord, is zero. That means that in a cord, or a wire, a metal wire, which is just laying by itself, there is no force pushing electrons through the wire. It's just going to stay, they're just going to spread out along the conductor and they're just going to stay put. There's no potential for motion. So we call that an equipotential surface, and the wires in circuits specifically are going to be considered as equipotentials. Okay, now all that leads us to our three fundamental tools which we're going to use. This is affectionately known as KVL and KCL and Ohm's law. So KVL, Kirchhoff's voltage law, says that the sum of potential differences around a closed loop is 0. And you see why this is the case in a conservative field, right? Because it depends only on the endpoints. Well, if the endpoints are the same, then the voltage is going to be the same and the difference is going to be 0. So we're going to take advantage of that. Then KCL, Kirchhoff's current law, which says that if you have a junction, then what comes in must go out. So it's essentially a conservation law, right, which says that current going in equals current coming out. Last, we have Ohm's law, which tells us about the voltage drop across a resistor. So in any circuit, we're going to have positive terminals and negative or ground terminals. By convention, charge flows from positive to the lesser value, right? So the bigger value to the lesser value, positive to negative. And so we have a current going across this resistor, and we assume that the wire here and here are perfect equipotential surfaces, and that any potential drop, which happens from here to here, which it has to drop because here the potential is V, here the potential is 0. So it drops by amount of V across this resistor. We squeeze that all into one spot and we say that the resistor represents the instantaneous drop in voltage. And it can represent a power element in your circuit or just anything across which a voltage drop happens that's not a time-varying element like an inductor or a capacitor. So that's going to be our approximation there. And Ohm's law just tells us that V is equal to IR. The voltage drop across a resistor is equal to the resistance, which is a material property, times the current going through that resistor, I. Now let's use these rules to figure out the currents in this circuit. So in each branch of the circuit, you're going to have a different current. So we're going to have a current going through the battery and through these two resistors, right? Then we'll call this I1. Then we're going to have another current just going through this middle branch, which, since this is the positive terminal and this is the negative terminal, we're going to be expecting current to flow through like this and then split and both go down and come back here. And if you get the direction wrong, you'll just get a negative sign in your answer, but this is what we expect to happen. So this we'll call I3, and we'll call this one, which goes all the way around here, I2. Now what do we do? Well, first let's use KVL on this first loop. We're going to start here and we're going to go this direction all the way back to here, and we know that the sum of the potential differences must be 0, assuming conservative field, right? So we start here, then we gain V volts, right? Then we're going to drop across this resistor. By how much? Well, if we use Ohm's law, we know that V equals IR, so it's going to be I1 times R. All right. Then we're going to go down through here. Same thing's going to happen. We're going to go across another resistor. So the voltage is going to drop by, this time, I3R. You see a different current there in that branch. And then we're going to go across this last resistor, which is part of branch 1 again. So minus I1R again is equal to 0. And since our unknowns are actually going to be I1, I2, and I3 here, I'm just going to write this a little differently, rearrange this to say 2R, I1. Notice that these two become negative 2 I1R. So we have 2R times I1 plus R times I3 is equal to V. If you rearrange that equation, you get that. All right, that is our first linear equation. It's linear in I1 and I3. Now, for our second one, let's do the second loop. Well, let's write this again. Let's start right here and go this way. Well, since we're expecting current to go down through this third branch in the middle, then this jump is going to be a positive gain in voltage by the amount I3 times R by Ohm's law, right? Then we're going to drop again when we go there by I2 times R, and the same here and the same here. So minus I2R minus I2R is equal to 0. We can rewrite this just as 3R I2 minus R I3 is equal to 0. All I did was combine these three into one term, right? Negative 3I3R. Switch the I3 and the R around because our unknowns, it's nice to have last. And then we just put a negative sign on everything. All right, now our last one, you might think to use the loop rule again on the big one, but the big one is not independent from these two. So we're actually going to use KCL here, the current law, for our last equation. We need three equations to solve for three unknowns. So for this last one, we're going to pick this junction, and into it we have I1 going, and out of it we have I2 and I3. That means that I1 has to be equal to I2 plus I3, right? Pretty simple. Or we can rewrite this as I1 minus I2 minus I3 is equal to 0. All right, so now we have three equations and three unknowns, and we can put this into augmented matrix form and start solving using Gaussian elimination. Okay, so now I've written our system of linear equations up here, and you can see the coefficients that go into the augmented matrix. And now we just row reduce and put it into row echelon form. So what should we do first? Let's switch row 3 and row 1 first. So let's start over here. Switch those two. We'll have 1, negative 1, negative 1, 0. 0, 3R, negative R, 0, and 2R, 0R, V. All right. Now let's multiply rows 2 and 3. We're going to do two steps at once here by a non-zero constant. Namely, we're going to divide row 2 by 3R, and we're going to divide row 3 by 2R. So if we do that, we'll have 1, negative 1, negative 1, 0. 0, 1, negative 1/3, 0, and 1, 0, 1/2 V over 2R. You follow? All right. So now, for the next step, what shall we do? Let's add the negative of row 1 into row 3 so we can get rid of this 1. So we don't want any 1s below other 1s. So we have same row 1, same row 2. Then we're going to have 0. Negative of that is positive 1. Positive 1 plus 1/2 is going to be 3/2, and this is going to stay V over 2R. All right. What next? How about we take the negative of row 2 and add it to row 3 so that we can get rid of this 1 down here. All right, if we do that, what will we have? We will have 0, 0, and then we will have positive 1/3 plus 3/2. So 1/3 plus 3/2 would be 2/6 plus 9/6, which would be 11/6. So 11/6, it's hard to say. And then V over 2R again. All right, and one more step to put it into row echelon form. We just need to divide out this last row by 11/6. And that will give us 1, negative 1, negative 1. 0, 0, 1, negative 1/3, 0, 0, 0, 1. And what is V over 2R divided by 11/6? It's going to be times 6 over 11. We will have 3V over 11R. All right, so now our matrix is in row echelon form, and we can use back substitution to solve the system of linear equations. All right, so we're going to have I1, according to the first line, minus I2 minus I3 is equal to 0. For the second line, we're going to have I2 minus 1/3 I3 is equal to 0. And for the last one, we're going to have I3 is equal to 3V over 11R. So we already know what the current in branch 3, that middle branch, was. It is the value of 3V over 11R, and that's in amps. All right. So let's plug that value in here and see what we get for I2. I2 is equal to positive 1/3 times 3V over 11R. That is going to be equal to just V over 11R. All right, and now I1 is equal to the sum of those two. Recall, when you add 2 and 3 together, you get 1 by Kirchhoff's current law. So that'll be V plus over 11R plus 3V over 11R is equal to 4V over 11R. So if we wanted to write our final answer as a coordinate triple, we could write, I'll just, for brevity, pull out the V over 11R as a factor, if you will, and we'll have a coordinate triple of 4, 1, 3. And these are our values for the different currents. We've solved an applied problem using Gaussian elimination and back substitution.